It'll help start our thinking of this unit if we start off by drawing a picture of an airplane and show all of the forces that are acting on it. Pause this presentation for a minute, and in the top corner of your notes, just draw a quick little sketch of an airplane and show what are the different forces that are acting on that airplane. Now that you have that little sketch, and we will come back to it as we go through this lesson, let's start with some definitions. First, a force. A force is simply a push or a pull that's acting on an object. Forces can be contact forces. That's when things are actually in contact with each other, when one object touches another and pushes or pulls on it. An example would be, in the picture shown here, the person pushing the luggage cart is exerting a force on the luggage cart by touching it. That's a contact force. There are also forces that act at a distance. We call these non-contact forces. Objects can exert forces on each other, that is, pushes or pulls on each other, even if they're not touching each other. For example, gravity. If I hold a ball up above the surface of the earth and let it go, the force of gravity pulls that ball towards the center of the earth, even though the ball and the ground aren't touching each other. Other examples include magnetic force. You know this if you've ever brought a magnet near a magnetic surface. You can feel the pull of the magnet before the magnet actually comes in contact with the surface, as well as static charges. These are forces that can act at a distance. An applied force is just something when something is pushing or pulling on an object. It's the force that you apply to something. For example, the motor pushes a car along. The motor is ultimately what causes a car to go forward. The motor generates the applied force to make the car move. When your mom is mowing the lawn, she's pushing the lawnmower across the grass. She's applying a force to the lawnmower. A normal force is the force that the surface of one body exerts on the surface of another body. Please note that in this unit, when we talk about bodies, we're not talking about arms, legs, and heads, not that kind of a body. In the context of physics, a body simply means a contained object. So it might be a lawnmower or a brick or a person. So in this case, it's the surface that one thing, the force the surface one thing exerts on the surface of another thing. The example shown below here, if a block is resting on a table, the normal force is the force of the push of the table up on the block and is equal to the block's weight. So the block is pushing down on the table is applying a normal force back up. It's pushing back up on that block. A good way to think about this mentally is to think of it as the support force. A normal force is often the force that's holding something up. Now, that's not always the case, but that's often a helpful way to think of it. Friction. Friction causes mechanical energy, that is the energy of moving things, to turn into heat energy. So for example, friction on a sled. We have these chickens riding down the ski slope on a sled. I don't know why the chickens are riding on a sled, but there it is. Friction is acting in the direction that is opposite of their motion. So if they're sliding downhill, friction is pushing back uphill. Friction always opposes motion. It always tends to want to slow things down, and it always generates heat. An easy way to tell the effect of friction is if you take the palms of your hands and rub them together really, really quickly, you'll see that you can feel the warmth from that. That's turning the mechanical energy of your moving hands into heat energy. An elastic force results from the changing of shape of something. So the two pictures here of the tennis ball and the silver sparkly ball, those aren't deflated balls. Those are balls that are in the middle of a bounce. So if you watch a video, you can actually see that the ball comes down, and when it hits the floor, the shape of the ball changes, it deforms. Then that change in shape of the ball pushes back against the ground, and that's what causes the ball to bounce back up. In your mousetrap cars, the elastic force comes from changing the shape of the spring in the mousetrap itself. When you set the mousetrap, what you're doing is you're bending the spring that's in there. And then you can use the force that comes from that bent spring to make your car go forward. The next thing we want to look at is gravity. Gravitational force acts along a line between two bodies. Typically, we think of gravity where one of the bodies is a planet. So, for example, there's a force of gravity attracting the moon to the Earth. The force of gravity acts along a line that connects the center of those two bodies. So the center of the moon towards the center of the Earth. It is that force of gravity between the Earth and the moon that prevents the moon from flying off into space, that holds it in orbit. The force of gravity also acts on all of the objects on the surface of the Earth and it pulls them down towards the center of the Earth. This is why even if you live in the southern hemisphere, you don't fall up.
Friction is a force to be reckoned with. On the road, in the air, and on water, vehicles fight friction to get going. They already face an uphill battle. Objects at rest tend to stay that way. That's inertia. Perhaps we can all relate. Engines give vehicles the jump start they need, but friction fights back. Friction is the force that slows down the movement of one surface over another. The road slows the wheel. The water slows the boat. The track slows the train. And air slows them all. Even inside the engine, friction makes it tough. A car uses about 20% of its engine power just to overcome friction in the moving parts. The hovercraft makes short work of friction on land and water. While a back engine thrusts this hovercraft forward, a front engine pushes a cushion of air down into the rubber skirt it rides on. Less resistance or friction than from the bottom of a boat. The hovercraft can even conquer snow and ice at speeds up to 70 miles per hour. Air might offer less friction than land or water, but it can be a real drag if you're a race car driver. Drag happens when air slows the motion of an object. A car with too much drag uses too much fuel and works too hard to accelerate. Drag race cars slice through the air to get going fast. On the other hand, air's friction is harnessed to keep cars on the ground. Tasman race car designers use something called downforce to stabilize them. Like airplanes, these Tasman cars have wings, but they're positioned in front and at the back. This keeps light, aerodynamic race cars in contact with the track at high speeds, even upside down. Air can create disastrous amounts of friction for vehicles at high speeds. When the space shuttle re-enters Earth's atmosphere, friction between air and the hurtling spacecraft would cause it to burn up if it wasn't protected. The space shuttle's specially made aluminum tiles protect it from temperatures as high as 2,500 degrees Fahrenheit. In the future, new forms of transportation will still have friction to contend with. But as engineers find new ways to defy it, it becomes easier for vehicles to slice through the air, walk on water, and defy land, even carry us beyond our atmosphere.
So let's come back to that picture you drew at the beginning that showed the multiple forces acting on an object. So we drew an airplane, and generally we'll draw 4 typical forces acting on an airplane. The first is gravity that tends to pull the plane back down towards the Earth. A force that counteracts that is the lift. That's the upward force that comes from air flowing over the airplane's wings. So when the lift is greater, the plane moves up. When the lift is lower, the plane moves down. Thrust is the force that comes from either the propeller or the jets that causes the plane to move forward. That's an applied force that comes from the airplane's engine. Drag is the force of friction from the air that causes the plane to slow down. If there's more thrust than there is drag, the plane will speed up because there's a greater force pulling it forward than slowing it down. If there's more lift than there is gravity, the plane will rise, the plane will go up. The net force is what we get when we add up the forces acting on an object, when we add up all of those forces. So for example, the net force on this teddy bear might actually be 0 because there are two equal and opposite forces, one from the girl pulling to the right and one from the boy pulling to the left. Forces that are acting in opposite directions but have the same magnitude will cancel each other out. So if the teddy bear is being pulled with equal force to the left and to the right, those two forces in opposite directions cancel each other out, and the net force on the teddy bear is 0. If the girl is stronger and is pulling with more force towards the right, the net force will be acting towards the right. In a force diagram, we'll use an arrow to show both the direction and the magnitude, that is the size of the force. So for example, a big arrow pointing towards the right might represent a strong push to the right. But a smaller arrow pointing to the right, that would represent a weaker push. So the length of the arrow corresponds to the size of the force. And the direction of the arrow shows the direction that the force is being applied in. So what's shown here is two forces with equal magnitude. They're both strong pushes, but one's going to the right and one's going to the left. Here's an example of how we would use a force diagram. Here's a person pushing on a large block. We want to show all of the forces acting on that block. So the first is the applied force. That's the force that the person is using, the force the person is applying to push that block to the right. Next is the force of friction that is acting against that applied force. So for the block to move, the person has to push strong enough to overcome friction. Then there's the weight of the block pushing down. That's the force of gravity pulling down. Is there any force that you notice that's missing in this case? Well, it's not drawn here, but it is implied that the block and the person are not simply free falling through space, that this is in fact a person pushing a block along the ground, and so there would be a normal force there from the ground that is pushing back up on the block. The units of force are the Newton. Remember, kilogram is a unit of mass. Force is measured in a different unit, and that is the Newton. There is a relationship between kilograms and newtons, but we need to wait a few lessons until we learn Newton's second law to figure out what it is. For now, it's helpful for you to know that a force of 1 Newton is approximately 1/4 of a pound. So if you were to take a 1/4 pounder sandwich and hold it in your hand, the force of gravity pulling that sandwich down would be about 1 Newton.